let's talk about RC time delay circuit. And in this circuit, we're going to be using resistors, capacitors, and transistors to see what we mean by time delay circuits. So, have you ever seen a situation where an output delays before it comes on, or delays before it turns off? So, all those characteristics are what is obtainable by a time delay circuit. So, let's begin by adding our resistor and adding our capacitor. Don't forget, this sign means this is the minus negative side of this capacitor, and I'm now going to add a resistor, another resistor. Then a transistor to turn on a LED. This can actually be anything other than a LED. So what we want to build now is a circuit that turns on after some seconds. Another resistor. And my LED. Okay, I need a battery. I can use this. Let's use 3 batteries. So let's connect the circuits. Let's start from the positive lines. Like that. The negative lines. Okay. Then the signal lines, I can use any of these colors. Now, this is where the RC circuit is formed. Now, the connection between here, the connection between here and here is what is an RC circuit. It's a series RC circuit, and this is what determines a time delay. The value of this resistor and capacitor determines how much delay we are going to get, and we are going to see that in experiment very soon. Let's connect this. Okay, let's change these values to 20 ohms, and let's change this to like 22k. Now let's change this to 100 kilo ohms and this to 1000 microfarads. Now the expected behavior of this simulation is that this LED should first be off, then it will turn on after some time. Let's see if that is correct. You see it's off, then after some time it should turn on. Let's see. 9 seconds gone, 10 seconds. See, it's turning on gradually. 14 seconds. It's turning on gradually. 17, 18, 22 seconds. And I think it's fully on now. Do you see that? So that's a simple delay circuit to turn on. Do you get that? To turn on. To turn on a LED. Now, what if I want to reduce how long it took for it to turn on? I can just reduce the value of this capacitor. If I reduce it to 100, let's see, you see it's going to be faster. You see now, under 4 seconds, it's already fully on. If I make it 10,000 microfarad, oh, let's not just push it too far. Let's make it 2200 and start simulation. Watch out for the time and when the LED comes on. 4 seconds, 7 seconds, 8 seconds, 10 seconds, 12. The LED is not on yet. 15. Yeah, it's beginning to come on now. It's beginning to come on. It's coming on gradually. It's coming on gradually. 30 seconds. It's halfway on. It's halfway on. And by around 40 seconds, it's almost fully on. Let's see how we can understand what is actually going on in this circuit. Let's attach meter, a multimeter. I'm going to put one to monitor the voltage at this junction. I'm going to put the other to monitor the voltage at the collector here. So I'll connect this one here. The other goes to ground, right? So attaching this meter will help us understand what is actually going on in the simulation circuit. You know, earlier I told you that a transistor requires at least 0.7 volts to turn on. So we will know when this voltage across this resistor capacitor crosses 0.7 volts. And then we also see what is going on at the collector here. So let's start the simulation. You can see the voltage is rising. 3.16 volts here means that the transistor is off. See, the voltage is rising gradually. So this is to depict that this capacitor is charging up internally. It's charging up until the voltage begins to cross the 600 millivolts or 0.7 volt barrier. That's when this transistor, you see the transistor voltage is also reducing now. It's coming down. At around 700, it's on. The transistor is already on, but it's not fully on. Do you see this? You see what is happening internally in the transistor now? So the voltage keeps charging up. At around 1 volt. So the transistor is on, but not yet fully on. Because when it is fully on, the voltage at this collector should be less than 1. It should be around 0 point something, 0 point something, 0 point, maybe 0 0.05, 0 0.5, 0 0.2 volts. At that junction, the transistor is fully on. You see how long it takes for it to finally come on. So this is simple RC circuit. Now let's do it in the reverse direction. What if we want this load to go off after some time? That is, whenever you first put it on, it turns on, then after some time it goes off. A simple thing I can do. There are 2 ways we can do this. We can take out the output of this and feed it back to another NPN transistor, or we can just remove this transistor and replace it with a PNP transistor. So if we replace it with a PNP transistor in this manner, the collector goes to ground, the base to this resistor, the emitter to this junction, and oh, sorry about that. And the collector to ground. So let's see what happens in this circuit. Play. You see the lights already on. So the light will stay on and begin to go off gradually after the is it 40, almost 48 seconds. Let's see if it works. Oh, I didn't remember to join this junction. You see it's going off gradually now. It's going off gradually. It's going off, still going off, still going off. Okay, so this may be the lowest points it can be able to get to, and I will explain why. Let's stop the simulation. Let's attach this meter correctly, and let's start again. So to shorten our simulation time, let me just reduce this back to like 1000 and start simulation. So you see the voltage So you see now it's almost off. It's almost off. So this is a reversal of the first circuit we first made, and it took almost 1 minute for it to go off entirely. Do you see that? So this is a simple time delay circuit. Alright, in the next video I'm going to be showing you how to use time delay circuits in 555 IC to generate oscillations. So RC circuits are also, they are the fundamental building blocks of oscillators. In the next video I'm going to be showing you how to use RC circuits to generate oscillations, to convert DC to an alternating current. Thank you very much, and see you in the next video.